Hi everybody, in this video we're going to talk about the sum and product rules for probability, and don't worry, the probability that my wife will try interrupting us again is very low. So let's start with the sum rule, which says that when we have two events, A and B, the probability of A happening or B happening, so either one is okay, is equal to the probability of A plus the probability of B. And this rule only applies when events A and B are mutually exclusive. That means that they cannot happen at the same time. Okay, so let's take a look at an example. And actually, I'm going to solve this problem in a different way before looking at this rule. And then we're going to go back and see how we could have solved it using this rule. So a spinner has one green space, it's right over here, two pink spaces here and here, two blue spaces, two purple spaces, and three orange spaces. What is the probability that the spinner will land on either orange or green? So let's say we're in some kind of contest and we spin this spinner and the arrow goes around and around and around. And if it lands on orange or green, either one is okay, we win the game. So what's the probability of that happening? Well, let's go back to our favorite probability fraction, which is good over total. So the probability that this lands on orange or green, I wrote green first, that's okay, is equal to, right, probabilities are always good over total. What do I mean by good? Well, we have to figure out how many orange and green spaces there are, either one, okay? And I can see that there are three orange spaces here, so I'm going to write a 3 in the numerator. And I also see that there is one green space. It also said it over here. So I'm going to add 1 in the numerator, and I'm going to put that over the total number of spaces, which, let's see, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or another way we could have gotten that would be to add these numbers. One green space, so 1 plus 2 is 3, plus 2 is 5, plus 2 is 7, plus 3 is 10. Okay, and there is our probability. 3 plus 1, of course, is 4. So our probability is 4 over 10. If you want to reduce that, you can divide, in this case, 4 and 10 are both divisible by 2. So if we just wanted to simplify this, we could say that the probability is 2 over 5. Okay, and then if you do 2 divided by 5 or 4 divided by 10, you'll get 0.4. And if you want to turn it into a percentage, move this 2 decimal places to the right, and you would get 40%. So here we have it written as a fraction again in simplified form, as a decimal, and as a percent. All of those mean the same thing. So this would be unlikely, not super unlikely. You can see that a bunch of the spaces are good for me, but it's still unlikely because the probability of it happening is less than 50%. Okay, so that's how we can find the probability of landing on either green or orange, okay, just using our good old good over total formula. Now, what about this rule here, though? I didn't use this at all. So let's see if we can figure out where this rule comes from. Let's take a look back over here where I wrote 3 plus 1 over 10. Now I'm going to write that in a different way, and I want you to look at this, and I want you to make sure that what I'm doing here is okay. So I'm going to write it this way. Instead of writing 3 plus 1 over 10, I'm going to write 3 over 10 plus 1 over 10. Okay, I want you to pause the video for a second and think, is this a valid way of writing this? Is what I wrote over here actually equal to what I wrote over here? Are they the same? Okay, and the answer is that they are the same, because how do you add fractions? If I have two fractions here and I see that the denominators are the same, how would I add those? Well, I would add the numerators together, so I would do 3 plus 1, and whatever 3 plus 1 is, that would be my new numerator, and I would then just keep the denominator the same. Okay, if I'm adding fractions and the denominators are already the same, I would just keep the denominator the same. So if I started with this and I wanted to add these two fractions together, then my result would just be 3 plus 1 in the numerator, which is of course 4, and I would still have a 10 in the denominator. Okay, so these two expressions, this one and this one, are in fact equal to each other. Now, why did I write it this way? Because you might notice that 3 over 10 is just the probability of landing on orange, right? So forget about the green for a second. There are 3 orange spaces. And so if I wanted to calculate just the probability of landing on orange, I would write that as 3 over 10 because there are still 10 spaces total. Okay, now what about this over here, 1 over 10? What would that be? Well, there's just one green space on the spinner, right? And there are 10 spaces total. So 1 over 10 is the probability of simply landing on green. So 1 over 10 here, I can write that as the probability of landing on green. So what I have on the right side of this equation here is actually the probability of landing on orange plus the probability of landing on green. Okay, and of course that is equal to this, which we already said was the probability of landing on green or orange. Okay, so what we have here, what we just figured out is the probability of landing on green or orange is the same as the probability of landing on orange plus the probability of landing on green. Okay, now that is true in general. If I have two events, A or B, and either one of them is okay, then the probability of A happening or B happening is the same as the probability of A plus the probability of B. And this is, again, only applies when events A and B are mutually exclusive, right? So they can't happen at the same time. If you look at that spinner, can I land on orange and green at the same time? No, I'm either going to land on an orange space or I'm going to land on a green space. Okay, we're not going to talk about what if I land right here between orange and green. Okay, we're not going to worry about that. It's either orange or green or something else, but they can't happen at the same time. So going back to the beginning of the problem now, if I had wanted to use this rule from the very beginning, here's how I could have done it. I could have said, well, the probability of picking orange is 3 out of 10. The probability of picking green is 1 out of 10. And therefore, the probability of picking orange or green is the probability of picking orange plus the probability of picking green, which is 3/10 plus 1/10, which of course is 4/10. Okay? All right, now I also want to point out that even though two things are good for me, landing on an orange space is good and landing on a green space is good, when we're doing probabilities like this, we're only talking about doing one action. So in other words, I'm only flicking that spinner one time. I'm flicking it once, it's going to go around and it's going to land somewhere. Okay, and I'm happy if it lands on orange, and I'm also happy if it lands on green, but I'm only going to flick that spinner one time. Okay, and that's important because for some of the other problems that we're going to do, when we talk about the probability of one thing happening and another thing happening, we're actually going to be doing two things instead of just one thing, like I'm flicking the spinner just one time over here. Okay, so now with that said, let's move on to the next example. And for this one, we're going to talk about the product rule. Notice here that I put the word "and" in red letters. Back here, I put the word "or" in red letters because I want you to pay attention to that. The probability of picking A or B is the probability of A plus the probability of B. And as we're going to find out now, The product rule says that the probability of A happening and B happening. So we're actually going to be doing two different things when we have problems like this. In this case, I'm going to be pulling a marble out of a container, and I'm also going to be picking a card. So I'm going to be doing two things, and the probability of event A happening and event B, which we'll say what events A and B are in a second, is going to be the probability of A times the probability of B. So just remember, if it's A or B, then we're adding the probabilities. If it's A and B, then we're multiplying the probabilities. Okay, so that's the product rule. And this rule only applies when events A and B are independent. So remember what independent means. That means they have nothing to do with each other. Okay, one thing happening does not affect the result of the other thing in any way. All right, so let's look at this problem here. A container holds one purple marble, okay, right there, 2 orange marbles, and 3 green marbles. A stack of cards contains one queen, so it's a very small stack of cards. It's only 3 cards. It contains 1 queen and 2 aces, all right? So imagine that we have this container here and we're mixing it up and we're not looking, and we're gonna reach in and pull a marble out, okay, randomly. So we don't know which one we're going to pull out. And the same idea with the cards. Imagine that we have those cards and we're going to shuffle them up and then close our eyes and pick one, okay? What is the probability of selecting a green marble and an ace? So keep in mind, 2 things are happening here. One is that we're reaching into this container and picking out a marble. And then the other action that we're doing is we're picking one of those cards from the deck, okay? So it's 2 things that are happening here, unlike before where we were just spinning that spinner one time, even though 2 different colors were considered good. Here we actually are doing 2 different things. Okay, and we want to figure out the probability that we reach our hand and pull out, what do we want? We reach our hand and pull out a green marble, and that we get an ace over here. So imagine that you're at a carnival or something, and you have to perform these 2 tasks. And if you do both of them, then you'll win a prize. You'll win a big stuffed animal or something like that, okay? So maybe you reach your hand into this container and you pull out a green marble, right? You look at it, oh my goodness, it's a green marble. I won. But no, you didn't win yet, because then the guy, the carny, okay, behind the counter, he tells you, wait, you didn't win yet. You also have to pick an ace out of here, okay? So then maybe you close your eyes and you try to pick an ace, and oh, it was the queen. So you didn't win. So both of these things happening is actually harder than just one of them happening. We want to figure out the probability that we succeed both times here. So let's try to figure that out. So the probability of picking what do we want here? A green marble, and then when we select from the card here of getting an ace. What's the probability of that happening? Well, we could use this product rule, but I don't want to just tell you what that rule is and then use it. I want to explain to you where that rule comes from. So first we're going to figure this out just by doing our good old good over total. Okay, so now in this case, since there are 2 things going on here, when we talk about the total, we're talking about the total number of possible outcomes. Okay, so we want every combination of picking a marble and pulling a card. So for example, we could pull out this orange marble and pick the queen, or we could pull this orange marble and pick the queen, or we could pull this orange marble and pick this ace over here, or maybe we pull out this green marble and pick this ace, or this purple marble and pick this ace, or this green marble and pick this queen. Okay, so there are a lot of different combinations of things that could happen. Now, if you remember a couple of videos back, we learned a rule for figuring that out? So how many different combinations are possible here? Well, we'll just use the counting principle. The counting principle tells us that if this can happen in 6 different ways, 1, 2, 3, 4, 5, 6, and this can happen in 3 different ways, 1, 2, 3, then the number of combinations that are possible are 18, because that's 6 times 3. Okay, so the counting principle says if one thing can happen in m ways and the other thing can happen in n ways, then the combination of outcomes is m times n. In this case, 6 times 3. So let's put down here in the total 6 times 3, okay, in the denominator, which is where we want to put the total. Now, how many good combinations are there? This is the number of total combinations, 18, okay, 6 times 3, but not all of those combinations are good. So for example, if we pick a green marble and then pick the queen, that's no good. The guy behind the counter is not going to allow us to win. If we pick the purple marble and pick an ace, that's also no good, okay, because the ace is good, right? But we don't want a purple marble, we want a green marble. So the only combinations are picking this green marble and this ace, or this green marble and this ace, or this green marble and this ace, and so on. So how can we figure out the number of good combinations there are? Well, again, we would use the counting principle, but only for the good stuff. So in this case, the green marbles are good. And how many of them are there? There are 3 green marbles, and we have to multiply that by how many good cards there are. And how many are there? Well, we like aces, and there are 2 aces, 1, 2. So we're going to multiply that by 2, okay? And then we can just go ahead here and do 3 times 2 is 6, and 6 times 3 is 18, okay? And there is our probability. So the probability of us winning this game is 6 out of 18. Okay, if we wanted to reduce that, both of these numbers are divisible by 6, actually. 6 goes into itself. So we can reduce this, and we can write it as 1/3. We could write that as a decimal. It would be 0.3 repeating. I just realized that in a lot of these videos, I'm coming up with the number 0.3 repeating. That's just a coincidence. I don't mean for that to happen. Okay, or this would be approximately 33%. So it's still unlikely. We have a less than 50% chance of winning. It's still unlikely for us to win this carnival game, but it could happen. We could win. All right. Now let me go ahead and write this fraction over here a different way. So I'll just write it again down here. You know what? I like pink. I'm going to stick with pink. 3 times 2 in the numerator over 6 times 3 in the denominator. Hopefully you will agree that this fraction is the same as 3 over 6 times 2 over 3. Okay, because if we have 2 fractions, how do we multiply them together to get our answer? Well, we just multiply the numerators. So the numerator of our answer would be just the original 2 numerators multiplied together, and that's what we have here. And the denominator of the answer would be the original 2 denominators multiplied together, and that's what we have here. So hopefully you will agree that what I have written over here is really equivalent to what I have over here. Now, the reason I wrote it this way is because maybe you'll realize that 3 over 6 is just the probability of getting a green marble. We can see that there are 6 marbles total in that container, and 3 of them are green. So if I just wanted to figure out the probability of reaching my hand into that container and picking a green marble and forget about these cards here, that probability would be 3 over 6, or 3 divided by 6, which is a half, right? 0.5. So we can write over here that this is the probability of getting a green marble. And now what is 2/3? 2/3, well, I have 3 cards over here and 2 of them are aces. So 2/3 is the probability of picking an ace, okay? Just forget about the container now and just focus on the cards. 2/3 is the probability of picking an ace. So let's write that over here. So 3/6 times 2/3 is really the probability of picking a green marble times the probability of picking an ace. And that is equal to this over here, which we already said was the probability of picking a green marble and picking an ace. And we figured that out by using the counting principle in the numerator and the denominator. So I know that this over here is the probability of picking a green marble, and an ace. Okay, so what did I just learn? I learned that the probability of picking a green marble and an ace is the same as the probability of picking a green marble times the probability of picking an ace. Okay, and that is what the product rule says, that if we have two events A and B, the probability of A happening and B happening is just equal to the probability of A happening times the probability of B happening. So if we want to now go back to the beginning of the problem and do it again using this rule, then what we would need to do is say, okay, the probability of picking a green marble is 3 out of 6. The probability of picking an ace is 2 out of 3. The probability of picking a green marble and picking an ace is equal to the probability of picking a green marble times the probability of picking an ace, which is 3 over 6 times 2/3, which is 6 over 18, like we saw before. All right, now again, I want to emphasize that this product rule, it only applies when events A and B are independent. They have nothing to do with each other. So me pulling a green marble out of that container does not affect what I choose, the card that I choose at all. Okay, they have absolutely nothing to do with each other. If I pick a green marble, does that mean that I'm more likely to pick an ace than if I had picked an orange marble? No, of course not. This does not influence what happens here. So they are independent. And that's when we can use the product rule, when we have two independent events. And I want, again, to stress that these are two events. Okay, it's two things that are happening. We're picking a marble here and we're picking a card here. Okay, unlike back in this problem, which we did, where it was just one, we would just spun that spinner one time. So it was just one action that we were taking. Here, we're taking two actions, okay? Okay, now I'm going to I'm going to change this problem up a little bit. Instead of saying, what is the probability of selecting a green marble and an ace, I'm going to say, what is the probability of selecting a green or purple marble and an ace? So this problem has both the word or and the word and in it. We're actually going to be using both of these rules to solve this problem here. So let's write it this way. The probability of picking a green or orange marble. Okay, so that's one action that I'm going to take, is I reach my hand into that container and I just hope that I get a green marble, or no, I'm sorry, not an orange one, a purple one. Okay, but again, that's one action that I'm taking. I reach my hand into that container and there are two colors that I hope to get. Okay, either one of those is good for me, but it's still just one action, reaching my hand and pulling a marble into that container. But now I'm also going to do another action. I'm also going to pick one of these cards here and I hope that I get an ace. So I want to know the probability that I get a green or a purple marble with my first action, and that I get an ace with my second action over here. Now I can mix these two rules together, okay? And I can say, well, I can say that this actually, you know what, let me do it this way. I can say that I can sort of break these up and say that that's since I have an and here, which is splitting these two things up, I could say that that's the same as the probability of picking a green or purple marble times the probability of picking an ace. Okay, so what did I just do there? I just applied this rule over here. This word and over here is telling me that these are two separate actions. One action is I reach into the container, and the other action is that I'm pulling a card. And when I have a situation like that, I can apply this rule over here, which says that the probability of both of those things happening is the probability that I'm successful with my first action times the probability that I'm successful with my second action. Okay, and now I still see that I have an or over here within this probability, the probability of picking a green or purple marble. Now I can go back to the sum rule, and if I see that this is still just one action, I'm just reaching my hand into that container, but there are two different colors that are good things for me to get. When that happens, then I could say that the probability of this or this is the same as the probability of the first color of me getting one of the marbles, which is green, plus the probability of getting a purple marble. That's kind of weird how I said that. The probability of getting a marble which is green. How about a green marble? Okay, there we go. All right, so we have the probability of this times this is the sum of these two probabilities times the probability of getting an ace. Now, you might have noticed that I made a small error there, and my error is I didn't follow the order of operations. So if I write it this way, then that's telling me to multiply these first and then add this one. That's not what I want to do. So I actually want to add these first and then multiply the result that I get here with the probability of getting an ace. So what I'm going to do is I'm going to put these in brackets, which are exactly the same as parentheses, but sometimes you use these squared off brackets if you're already using parentheses. Otherwise, the only reason people do that is otherwise it just looks kind of messy when we have two curved parentheses right next to each other. So sometimes people like to write the brackets, but they're exactly the same as parentheses. Okay, so now we can just go ahead and do the math here. The probability of getting a green marble is 3 out of 6. The probability of getting a purple marble is 1 out of 6. Okay, 1 purple marble out of 6 total, times the probability of getting an ace is 2 out of 3. Okay, so let's see, 3/6 plus 1/6 is 4/6, and then times 2/3, and that's going to give me 8 over 18. Okay, which is a little bit better. My chance of winning improved a little bit. I don't know if you remember, but when we had just the green marble instead of the green or the purple marble and getting an ace, our probability was 6 out of 18. So our chances of winning improved by a little bit. Okay, 8/18 is a little bit more than 6/18. And that of course does make sense, because now not only is the green marbles good, but also if I get a purple marble, that's also good. So I have more ways of winning. So of course my probability of winning should improve. Okay, so let's continue to the next problem. The next problem okay, a container holds 1 purple marble, 2 orange marbles, and 3 green marbles. So this is the same container we saw before. You select a marble, record its color, and replace it, meaning you put it back in. So we're going to close our eyes, reach our hand into the container, pull out a marble, see what color it is, and make a note of it somewhere, and then put the marble back in the container and shake the container up. And then we're going to select another marble. So we're actually there are two actions that are happening here. One is selecting the first marble, and then the second action is that we're going to select the second marble. And between the selection of the first and the second marbles, we are going to be putting that first marble back in. what is the probability of getting a green marble on your first selection and a purple marble on your second selection? So these two events are independent. One has nothing to do with the other. If I get a green marble on my first try and then put it back in and I shake the container up again and then reach my hand in again, the fact that I got a green marble on my first try does not affect the outcome of what I get on my second try. So these are independent events here, and therefore we can use the product rule, the probability of A and B, okay, where A happens on our first action and B happens on our second action, is equal to the probability of A happening times the probability of B happening. So if I want to figure out the probability of getting a green marble on my first try and a purple marble on my second try, now rather than using the counting principle to find the number of combinations that are good in the numerator and the number of combinations that are the total number of combinations in the denominator, now we can just go ahead and use this rule, which is honestly easier. So that's going to be equal to the probability of finding a green marble times the probability of finding a purple marble. Okay, well, what's the probability of getting a green marble? That's just 3/6, because there are 3 green marbles and 6 marbles total. And we're going to multiply that with the probability of getting a purple marble, which is 1/6, because there's just 1 purple marble, and there are still 6 total marbles when we reached into the container the second time. Now, why are there 6 marbles in there still if we already took one out? Because after we took out the first marble, we put it back in, remember? So we took it out, we saw that it was green, but then we put it back in, so there are still 6 marbles in there. Okay, so this is a problem with replacement, it's called, when we pull something out and then we replace it. We put it right back in. So we're replacing it with itself, which is not much of a replacement, but technically it is, right? So that's a problem with replacement. And when that happens, these two events are independent. And so we can use this rule here. Later in the video, we're going to look at a problem where we pull a marble out and we don't replace it. And then the events that we're going to talk about would not be independent because, well, you know what? Let's just save that for later. But for this one is independent. We'll talk about the other example later where we do not replace the marbles as we pull them out. So let's just move on now to the next problem right over here. Excuse me. So I'm going to save, I'm going to actually bring this down a little bit. We'll save that for later. Whoops, there's Raul. We'll get to him in a little while. Okay, you have a deck of cards. This time, instead of jacks and queens and kings and aces, we have shapes here. So the shape on every card is a triangle, circle, or square. The color of every shape is either purple or yellow. How many of the shapes are square or yellow or both? Okay, so right now I'm just asking you how many there are. I'm not asking you the probability of picking something. We'll get to probability in a second. But right now I'm just asking a much simpler question. How many are there? How many of these shapes are either a square or yellow or both a square and yellow? Okay, well, let's just go ahead and see. We'll just circle them as we go. So this one over here is a square. Remember, we're looking for shapes that are square or yellow, or they could be both. So this one is a square, so we'll circle that. Squares are good. It's not yellow, but that's okay. As long as it's a square or yellow, or both, it's fine. This one is not a square, but it is yellow, so that one's good, so we'll circle that. This one is also not a square, but it's yellow, so we'll circle that. This one is yellow, that's good. This one is, let's see, it's not a square, it's a circle, and it's also not yellow. So it does not match any of our conditions, so I'm not going to circle that one. This one over here is not yellow, but it is a square, so we'll circle that. This one over here is a square, and it's also yellow, so it's both. We'll circle that one. And this one over here is a square, so we'll circle that one. Okay, so the number of shapes, so when I'm talking about a probability, I'll put P. If I'm just talking about how many of something there are, the number of something, then we can use the letter N. So the number of shapes that are squares or that are yellow is equal to, let's see, 1, 2, 3, 4, 5, 6, 7. Okay, so that was pretty easy. Now, what if somebody thought that they could answer this problem this way? Let me erase this for a second. So we know that the answer is 7. Okay, we already just looked at it and we saw it wasn't too hard, right? So there are 7 shapes that are either a square or yellow. But what if somebody said, you know what? In order to figure this out, I'm going to add the number of square shapes. Add that to the number of yellow shapes. Let's see if this works. So let's pretend that we don't know the answer yet. And now let's go ahead and circle the number of squares. That's a square. No, 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 no. Yes, that's a square. Yes, that's a square. Yes, that's a square. Okay, so that's 4. Okay, so the number of squares is 4. Now we're going to add the number of yellow shapes. So let me erase this again and count how many are yellow. 1, 2, 3, 4. Okay, so there are 4 yellow shapes. All right, and 4 plus 4 is equal to 8. Now, wait a minute. Wait a minute. We already got the answer before. There were 7 shapes. You saw it. We counted them. There were 7 shapes that were both, well, that were a square or yellow or both. Okay, only 7, not 8. Why did we get 8 here? Where did we go wrong? Pause the video and try to figure out where we went wrong here. Did you figure it out? It's because of this guy's fine, this guy's fine, this guy's fine. Here's the troublemaker right over here. This shape is a square and it's also yellow. So it got counted twice. That's why we messed up. We added it, so it was, remember there were 4 squares. So one of those 4 was this guy over here, okay? But one of these yellow shapes was also this guy. So this guy got counted twice. So that's why our total number of shapes that were either square or yellow is 1 more than it should be. The correct answer is 7, but we got 8 this time. And the reason we got 1 more than we should have is because this one guy over here, this one shape over here was counted twice. Now, how can we rectify that? Well, what we can do is actually this formula here is not correct. If I want to figure out the number of shapes that are either a square or yellow or both, adding the number of squares and the number of yellow shapes is not the right thing to do. But what we could do is we could add the number of squares and the number of yellow shapes and then subtract the number of shapes that are both square and yellow. Okay, I'm intentionally not writing the word "and" here because I don't want you to get it confused with this rule. What we're doing is we're finding the number of shapes that are both squares and yellow. So in this case, we just have one shape like that. And we're going to subtract that from the sum of these two. Okay, because we had this square in here, so that's fine. But then when we added it In here also, we added it too many times. So in order to fix that, then we have to subtract it. All right, so let's see this formula now in action. So there are four squares. So I'm just doing this, we already did, but I'm doing it again. There are four squares. Then we're going to add the number of yellow shapes. And again, that's 1, 2, 3, 4. Now this guy thinks he's all slick because he got added. He got himself added twice, but we're wise to his game. So now we're going to subtract the number of shapes that are both squares and yellow. And how many is that? Well, there's just one shape, this troublemaker over here, which is both the square and yellow. So we're going to take that away. And when we do that, that fixes our answer so that we get 7, which we know is the correct answer because there are 7 shapes which are either squares or yellow or both. Okay. By the way, we're not always subtracting the number 1. That was just in this example. If we had done another example where, let's say, both of these guys over here. Oh, I can't. Let's just draw over it like this. Let's say that both of these. That doesn't look very good, but let's say I had 2 yellow squares. Let's see if our formula here would work. So what's the correct answer that we want to get? Well, I know that this one is yellow. This one is a square. This one's yellow. This one's yellow, yellow, not yellow or a square. This one's a square. This one's a square and yellow. And this one is also square and yellow. So we know that, again, our answer, if it had looked like this to begin with, our answer should be 7 again. Let's see if this formula works. Okay, so now let's circle the number of squares. 1, 2, 3, 4. It's still 4. And then we're going to add the number of yellow shapes. Let's see, how many shapes? Whoa, oh man. Okay, how many shapes are yellow? 1, 2, 3, 4, 5. So now this guy's a troublemaker, just like he was before. So he got counted twice, but now this guy also got counted twice. Now he got counted as a square before. He was one of the 4 squares, and he's now also one of the 5 yellow shapes. So now we have 2 troublemakers that got counted twice, but then this takes care of it. Because now, if we go ahead and count the number of shapes that are both squares and yellow, we found the troublemakers, and we're going to subtract them away. Okay, you can get counted once, but not twice. If you get counted twice, then you have to get subtracted once. So that's what we're doing over here. And 4 plus 5 is 9, minus 2 is 7. So it works. If we add the number of squares and the number of yellow shapes and then subtract the troublemakers that got counted twice, then we do end up with the correct answer for the number of shapes that are squares or yellow or both. So this is an example of, well, we didn't really talk about probabilities here, but we were talking about just counting the number of shapes. But you can see here that something can be a square and it can be yellow at the same time. In that case, the events are not mutually exclusive. Remember, mutually exclusive events cannot happen at the same time. We ran into a problem here because these things could happen at the same time. It is possible to be both a square and yellow. And in order to fix that, we had to, after we added over here, we had to subtract the number that were both a square and yellow. Now what I want to do is I want to take this formula over here and I want to divide both sides by something. Why am I doing that? Well, I don't have to do that. I just want to do that. This isn't something that we talk about so much. But if you have an equation, let me just pick something simple, like 1 plus 1 equals 2. Is that a true statement? Well, sure it is. What if I wanted to, just for the heck of it, what if I wanted to divide both sides by 8? Would I end up with something which is still a true statement? Well, let's see. 1 plus 1 is 2. 2 divided by 8 is 0.25. And here I also have 2 divided by 8. That's also 0.25. Okay, so I'm just giving you this example to show you that if we have something here where one side is equal to the other side, then you can do whatever you want to with it, actually. And as long as you do the same thing to both sides, then your result will still be a true statement. Okay, so what I want to do here is I want to divide both sides by the total number of shapes, or the total number of cards, right? Because all these, really, in the problem said I had a deck of cards. So I want to divide both sides here by the total. Do I have to do that? No, but I want to. And I know that if these two things were equal to begin with, and then I do the same thing to both sides, then both sides would still be equal. So my result would still be valid. Now, if I have something plus something minus something all divided by something, then that's actually the same thing as taking each thing and dividing it individually by the total. Right? So just as another example, 1 plus 1 over 2 is the same thing as 1 over 2 plus 1 over 2. Okay, 1 plus 1 is 2, divided by 2 is 1. 2 divided by 2 is 1. And then 1 divided by 2 is a half. 1 divided by 2 again is a half. And then a half plus a half is 1. Okay, so I still end up with a true statement. I still have the same thing on both sides. Okay, so what I did there is I took my original statement that the number of shapes that are both square or yellow or both is equal to the number of squares plus the number of yellow shapes plus the number that are both, and then I divided both sides by the total, and then I just rewrote that with putting the total underneath each one individually instead of underneath the whole thing like that. Now, why? So what I end up with here is still a valid statement. Now, why am I doing it this way? Because what happens if I take the number of something and then divide by the total? What I end up with is actually a probability, right? Because what's the probability? What's the definition of a probability? It's good over total, I like to say. But when we say the good in the numerator, we're really just talking about a number of something. So if we're taking the number of something and dividing it by a total, by definition, that's giving us a probability. If I take the number of shapes that are both squares or yellow, and I divide it by the total, that's giving me the probability of finding a shape which is either a square or yellow. If I take the number of squares and divide it by the total, that's giving me the probability of finding a square. Okay, and this would be the probability of finding a yellow shape. And this would be the probability of finding a shape which is both a square and yellow. So now you see where this rule comes from, right? We started with this over here, and then if we just take this, and remember we had to include this minus this term over here to account for the troublemakers. And then if we take this over here and just divide it both sides by the total, what we get is exactly this formula over here. So when two events are not mutually exclusive, right? This rule over here was just for the when two events were mutually exclusive. Then to find the probability of A or B, we just add the probability of A with the probability of B. But when two events are not mutually exclusive, then to account for those troublemakers, we have to subtract the probability of both event A and event B happening. So when events are not mutually exclusive, so if they can happen at the same time, like being a square and being yellow, then to find the probability of event A or event B happening, we add the probabilities of events A and B together and then subtract the probability that both of them are happening at the same time. Now, using the magic of computer editing or video editing, I just changed this question a little bit. So instead of asking how many shapes there are, I said, what is the probability of selecting a shape that is a square or yellow or both? So again, we're just taking one action. When you have a probability like this with or in it, you're just taking one action. In this case, the one thing that I'm doing is I'm just reaching my hand and selecting a card, one of these cards over here, but I'm only going to do that once. But there are two things which are good. Being a square is good and being yellow is good. But in this case, something can be a square and yellow at the same time. So in order to figure out that probability, I would have to use this rule over here. And it's very similar to what we did before. So the probability of being a square, yellow, or both, well, the probability of being a square is we find the number of squares that there are and divide by the total. So there are 1, 2, 3, 4 squares out of a total of 8 squares, so 4 over 8. And then we add the probability that I pick a yellow square, a yellow shape, not necessarily a square. So that would again be 4 over 8, still a total of 8. 1, 2, 3, 4, 5, 6, 7, 8. But now I have to subtract the probability that what I picked is both a square and yellow. This one's back to being purple again. So I have just one shape which is both a square and yellow. The probability of me picking that one shape is 1 out of 8. You can see it's very much the same thing that we did before, except now we have the totals in the denominator. Okay, and now we can see that the probability that I pick a square or something which is yellow is 4/8 plus 4/8 minus 1/8. And that's going to give me 4. So the denominators are just going to stay the same, right? And then the numerator, 4 plus 4 is 8 minus 1 is 7. So I have a 7 out of 8 chance of picking a shape which is either a square, yellow, or both. I feel like I've said that over and over and over again. Square, yellow, or both. Square, yellow, or both. Remember that. It's hard to say that. All right, and if we want to write it as a decimal, we could 7 divided by 8. That would be, let me put it over here, 0.875, right? Just for practice writing this in a number of ways. And then if I move that 2 spaces to the right, that would give it to me as a percentage. That would give me 87.5%. So it is very likely that I do pick a shape which is either a square, yellow, or both. Okay, 7 of those shapes meet that description. The only one that I don't want to pick is this one over here. All right, let's move on now. Ooh, yay, now I get to tell you why this guy was here. Yes, let's see. So we talked about, just to sort of review a little bit what we did, in the beginning here, we talked about the sum rule for events which are mutually exclusive. They cannot happen at the same time. Then, for the last few minutes, maybe more than a few minutes, we were talking about how to calculate the probability of events which are not mutually exclusive, which can happen at the same time. All right, now we're going to do something similar for the product rule. Earlier, we said when two events are independent, meaning they have nothing to do with each other. So one happening does not affect whether or not the other one is going to happen. So when they're independent, we can use this rule. The probability of A and B is equal to the probability of A times the probability of B. Okay, just multiply the two probabilities together. But now we're going to talk about what happens when we have events which are not independent, they are dependent. Okay, so when two events are not independent, we're going to use this rule instead of the normal product rule, which we saw a second ago. So this rule is the probability of A and B. So if A does influence what happens with B, then to calculate the probability of both of them happening, we would do the probability of A times the probability of B given A. Okay, now let me explain what I mean by that. Here we have Raul, and it is Raul's birthday. Raul says, "Hey everyone, hope you can come to my birthday party this weekend." Okay, great, sounds exciting. Let's scroll down a little bit and see who's planning on attending. Here we have Jennifer. Jennifer says, "Raul is having a birthday party. Sounds fun. I'll probably go." So the probability that Jennifer is planning on going, and the probability that Jennifer goes is, we'll say 0.9, which is very high. Remember, the very highest probability is 1. Can't get any higher than 1, because if something has a probability of 1, it's already certain. So it looks like Jennifer is almost certain that she's going to attend. The probability that she goes is 0.9, which is very high. Okay, so sounds like she's excited. Let's see who else is going. Oh, look, Mr. Friedman. He wants to join too. Raul and I are good buddies. I'll do my best to be there. So the probability that Mr. Friedman goes happens to also be 0.9. He's really excited about this party, and he wants to go celebrate his friend Raul's birthday. Okay, now let's scroll down a little bit more. There you see Mr. Friedman is still excited. Oh, maybe everyone will love the party jokes that he's planning on telling there. Okay, so the probability that Mr. Friedman goes is still 0.9 there. And looks like Jennifer is not so happy about something. Yuck, if that guy goes, I might just stay home with a good book. Well, I'm not sure what she means by that, but it looks like she's not too happy about Mr. Friedman, the idea of Mr. Friedman coming to the party. So if Mr. Friedman goes, that is going to influence her decision. So back here, she was really excited about going to Raul's party before she heard about anybody else going. The probability that she was going was 0.9, which is really high. But if Mr. Friedman goes, then it looks like here the probability went down to just 0.2. So the probability that Jennifer goes, given that so if Mr. Friedman goes, then the probability that Jennifer goes is going to drop down to just 0.2. So the way that we read this is the probability that Jennifer goes, given that Mr. Friedman goes, is 0.2. So she went from being almost certain of attending, being very likely to attend, to not so likely to attend once she heard that Mr. Friedman was going to the party. You know what? I think I see what's going on here. Jennifer just hasn't heard any of my amazing party jokes yet. If she heard the party jokes, then she would change her mind about me. She wouldn't feel that way. Okay, so let me think of a good party joke to tell Jennifer. I got one. What vegetables do sailors hate the most? You give up? Leeks! Okay, I see her point. All right, I'm just gonna stick with my day job here and continue teaching some math. So we would not be able to just, like over here, we can't just multiply the probability of Mr. Friedman going and the probability of Jennifer going. We have to take into account the fact that Mr. Friedman's decision is going to influence how Jennifer feels. So we're going to replace simply the probability of Jennifer going with the probability of Jennifer going given that Mr. Friedman is going. Okay, so scroll down a little bit more. So Mr. Friedman is going to decide first whether he'll go or not. Okay, Raul will call Jennifer to let her know what Mr. Friedman decided. Then Jennifer will decide. What is the probability that Mr. Friedman and Jennifer will both go to the party? Okay, so what's the probability that if you get to the party, you see Mr. Friedman there and you see Jennifer there? Well, in order to figure that out, we'll do the probability. In this case, the probability, so Mr. Friedman goes, that's like event A, and Jennifer goes, that's like event B. So the probability that this happens and this happens is the probability of Mr. Friedman going, or the way that I've been writing it, Mr. Friedman goes, probability that Mr. Friedman goes times the probability that Jennifer goes if she hears that Mr. Friedman is going. Okay, and hopefully you remember what those were so I don't have to scroll back up again. The probability, so Mr. Friedman is still excited about going. So the probability that he attends is 0.9, which is very likely. It's almost certain. We have to multiply that with the probability of Jennifer going if she hears that Mr. Friedman goes, which dropped from 0.9 when she had no idea who was coming down to 0.2 when she heard about that. Okay, so now multiplying these probabilities together, we would get 0.18, which is very unlikely. So it's still very likely that we would see Mr. Friedman at the party. The probability of seeing him is 0.9, okay, just that probability alone. But the probability of seeing Mr. Friedman and Jennifer both at the party is only 0.18. It's much lower, okay? All right, so that is an example of calculating the probability of two events when one event does influence the outcome of the other event. So they are not independent. Instead of just doing the probability of A times the probability of B, we have to do the probability of A times the probability of B given A. How likely it is for B to still happen if we know that A is happening. Okay? All right, so let's continue now with another example. This, I believe, is going to be our final example for the video. If you think it's difficult to watch an hour-long video, try making one. All right. So, this is very similar to something we saw earlier. A container holds 1 purple marble, 2 orange marbles, and 3 green marbles. You select a marble, record its color without replacing it. Oops, that should be a T. Without replacing it, meaning you do not put it back in, and then select another marble. You do this a few times. What is the probability of, what am I doing here? What is the probability of getting 3 green marbles in a row? Okay, so this is similar to a problem that we did earlier, where we reached into a container, we picked out a marble, and then we put it back into the container, okay? But now what's happening is we're doing this without replacing the marble. So we're going to reach our hand into the container, pick a marble, and then we're gonna put it off to the side somewhere, okay? And because of that, what happens first is going to influence what happens next, because when we reach into our container the second time, there aren't going to be as many marbles there. So picking the first marble out does affect the probability of picking the second marble out, okay? Because we're changing how many marbles are in that container. So these would not be independent events because one affects the other. These would be dependent events So let's try to figure this out. We are looking for the probability of getting a green marble on our first pick, and then a green marble on our second pick, and then a green marble on our third pick. So 3 green marbles in a row. Well, let's focus on the first green marble now. So we have that one's actually pretty easy. There's nothing complicated about that one. The probability that I get a green marble on my first try is just 3 out of 6, because there are 3 green marbles there. So there are 3 different ways that I could get a green marble, and there are 6 total things that could happen, 6 total marbles in that container. So that one was pretty easy. That's the probability of reaching in the first time and picking out a green marble. Okay, so far so good. Now we're going to have to multiply that by the probability of reaching in again and having the second marble also be green. Now you might think that you could just multiply that by 3/6 again, but if you thought that, then you're forgetting that we're not replacing that first marble. So let's say that we reached in and this was the first marble that we picked. That marble is not there anymore. Okay, we took it and then we put it to the side. So the probability now of selecting a green marble during our second pick is not going to be 3 out of 6. Now there are only 2 green marbles left. So we'll put 2 in the numerator, and there are 5 marbles total which are left. So we'll put 5 in the denominator. Okay, so this fraction over here is like the probability of event A being having our first marble be green. And this fraction over here is like the probability of event B given event A. So event B is that our second marble is also green. We want to know what the probability of that is, given that we already picked a green marble the first time. All right? And now, well, we want 3 green marbles in a row. So now we have to multiply this by the probability that our third marble will also be green. Now remember, after we picked the second marble out, we did not replace that either, so that's gone too. And now there's only 1 green marble left. So that's going to go in the numerator. And in the denominator, the total number of marbles that we have left, which is 4 now. Okay, what's this over here? This would be like, you know what, I'm going to change this a little bit. So the probability of A, and then B, and then let's call it C, a third option of now getting a third green marble. This right here is, I'm going to use this thing just to get this multiplication symbol. I have to do that. Okay. So that's going to be, that's like the probability. So say event C is getting that third marble. So now we're multiplying by the probability of this, of the third marble being green, given that the first marble was green and the second marble was also green. Okay, so we have these conditional probabilities here, right? So if you thought that we could just do 3/6 times 3/6 times 3/6, then you would be wrong. And what you would be forgetting is that there are less marbles there, and that changes the probabilities. So every time we reach into that container and pick a marble out, that affects the probability of getting the next marble and the next one and the next one, all right? As long as we are not replacing these marbles, we're not putting them back in. All right, so let's just go ahead and multiply these fractions together. I could simplify this, but I'll simplify it all at the end. Okay, so we would multiply 3 times 2 is 6, times 1 is still 6, and then 6 times 5 is 30, times 4 is 120. Okay, let's see. What can I do here? I can divide this and this by 6. Okay, and then I would get a 1 here, and I would get a 20 over here. Okay, so it's pretty difficult for this to happen. If this were like a carnival game and you had to pick 3 green marbles in a row, it's pretty unlikely that that would happen. You have only a 1 out of 20 chance of that happening. So it's not impossible, but it is unlikely. 1 divided by 20 is 0.05, and as a percentage, that would be 5%. So we would only have a 5% chance of being successful. Another way of thinking about that is if 100 people tried that carnival game, then you would expect about 5 of them to be successful and win the prize. Maybe not necessarily exactly 5, but that's the best prediction you could make. But you know what? I'm getting ahead of myself. That's for the next video. So anyway, I'm going to end this video right now, and have a great day.